My name is Scott Locke. I'm the moderator and the host of this track. My partner in crime here is Roberto Hernandez, who is a official title is Developer Extraordinaire for Inferno Red Technology. It's a small company I know a little bit about, and we work together there. And today, Roberto will be speaking about physical computing with .NET Core. He is as I mentioned, developer extraordinaire, working for Inferno Red Technology based out of Northern Virginia, building and architecting software for the last 18 years. He is a Microsoft MVP awarded back in 2007, 8, and 10, and an active participant of the Microsoft MVP Reconnect program. He's originally from the Dominican Republic, and he's a proud father of 2 beautiful daughters. And you can find him on Twitter at Hernandez Robert or on his blog at overridethis.com. And occasionally he posts to blogs.infernored.com as well. And a couple of housekeeping notes. As I mentioned, there's a live event Q&A that you can find within the Teams window, whether you're on the web or in the client. You can ask questions during the event, and we will have a Q&A session at the end. Roberto, you can also see these questions if you decide that you would like to answer questions during the event, during the session. That is your prerogative. If not, I'll wait to the end and I'll bring those to your attention. So with that, Roberto, take it away.
All right, so I guess the introduction is already done. Thank you, Scott. Like Scott said, I work for Inferno Red Technology, and I don't want to miss out on. I want to thank Inferno Red for providing me with the time to be able to do this sort of work, going out to the community and sharing content of fun stuff I do most of the time. Most of the stuff we do that I present on is not necessarily work-specific stuff. It's stuff that I spend a lot of time doing as a hobby. But ironically, eventually it leads to business opportunities here or there, so I cannot call it a hobby completely. So today we'll be talking about physical computing with .NET Core and a bit of a background on what that means. So physical computing in the past, and I guess we should establish first what is physical computing. So let me just jump into that first. So physical computing is a term that means a lot of things from my research that I just did in order to prepare this presentation. But the meaning that basically adheres to the content that I'm going to be showing us, it's the term most often used to describe the handmade art, design, or do-it-yourself hobby projects that use sensors and microcontrollers to translate analog input from a computer into physical actions on a device. So this could be lighting, could be servos, could be motors, etc. In my life, I gotta say, physical computing plays a big part. Like I mentioned, as part of a hobby, as part of work. We at Inferno Red have done a lot of prototyping lately of hardware that's actually for several startups in the IoT space. And also as a hobby, I fly FPV drones, and all the stuff that I just mentioned basically applies to them. They're full of motors, servers, lights, hardware, etc. And they're very fun to code against. Okay, so now that we established what is physical computing from the perspective of this presentation, let me go back to the previous slide just to basically explain why this is important. Physical computing with .NET Core, just a bit of the background on that. So traditionally, physical computing has been exclusive to, let's say, C++ developers, Python developers when the introduction of the Raspberry Pi came into place, and that expanded where Python became a first-class citizen in the world of microcontrollers. But .NET developers, Microsoft developers, unless we had background on C, C++, Python, we had a bit of a learning curve when it comes to transferring the knowledge that we already had in our day-to-day work to the work in the physical computing environment. Now, things got a little bit easier when Windows 10 IoT was introduced, because at that point, basically, we were able to carry the .NET knowledge that we had of .NET Framework and .NET Core into the mobile devices. But not all boards that are out there for microcomputing, physical computing, support Windows 10 IoT. So the next step to basically make it more broad and a reality when it comes to physical computing was write it against the .NET Core, which is basically a cross-platform at this point. So that is it. I mean, for me, it's definitely very exciting. It allows me to take all the work that I do day by day at work into the hobbies that I now do as part of extra time, or on the few projects that we have where we actually do IoT work. So what are we going to go a bit more into detail during the course of the slides? We're going to talk about what is a GPIO. Everything that we're going to do today goes against the GPIO. We're going to talk about the .NET Core libraries that have been built around interfacing with the GPIO. And we're going to do demos, lots of demos. So I don't have many slides. They do help me guide through the process of what I'm going to show you guys, but I basically like to see the code do the talking. So I'm just going to go ahead and exit. And we're still going to keep the slides here. But I'll go straight to the first topic, which is a GPIO. Now, a GPIO, and I put a couple of samples here on the slides, it's basically those ports, pinouts that we see on the, for example, this Raspberry Pi that my cursor is currently hovering over. They're not particularly assigned. They're basically there for you to use. And most of the time, they're binary. So most of the time, they're either on or off. Again, most microcontrollers have them. The original, I want to say, microcontroller that broke the market, the Arduino Uno, definitely has its sets of GPIO pins here. And this is a Arduino Nano, even smaller. And there is a Raspberry Nano version that's actually about this size, but this is basically the smallest in the market that you could actually get for a microcontroller like this, that it's already has a board, already has some features on it, and has a very usable GPIO stack. So those pins that are on a microcontroller that are considered to be a GPIO, again, they're basically binary. So if I wanted to say put an LED bulb on one of those Raspberry Pi pinouts, basically what I'm going to be controlling is the voltage that's going to be going out of that pin. That means that it can be either on or off. Some of those pins do support what is called hardware power modulation. In those scenarios, we can actually control how much power goes out of the pin. Usually on small boards like a Raspberry Pi or the Arduino Nano, those boards produce either 3 volts or 5 volts. But again, with power modulation, either at the hardware or software level, we can control what happens with that. And we'll see a couple of demos for that. The other things that this GPIO endpoints can actually be used for is for interacting with devices that are already out there. And I have a couple of those here on my desk. I included this camera view of my desk just because it was going to be very hard to do a presentation on hardware devices without showing you guys a little bit of the toys. So this right here is actually a device that supports SPI communication. This is a Raspberry Pi SenseHAD. So basically this would fit over the Raspberry Pi board, for example, this Raspberry Pi 4 that I have right here. And the device will interact with it using SPI protocol in order to manage the grid of LEDs that's on the top of that stack and manage a couple of sensors that are on that device, like the traditional environmental sensors, so like temperature, pressure, humidity. And also it has a gyro and an accelerometer, so you can measure motion. It's a very fun little board to play with. It is fully supported by the Microsoft libraries I'm going to show. It's just going to be done a little bit at the end if we have time. So other examples, and again, I have this little breadboard right here. This basically I did maybe 5 minutes before the presentation. If I cannot hook up an LED, then I shouldn't be doing this presentation, but there it is. Basic LED, and some of the work that I'm going to be doing basically is taking the GPIO outputs, hooking it up, and basically flashing some of those LEDs, interacting with the button on the board, etc. So what are these .NET Core libraries that I've been bragging about? If you look up in GitHub, github.com.net, that's a huge set of repositories that under the .NET umbrella. But if you basically go and simplify that search to be the IoT specific project, you'll notice that here we have what are called the .NET Core IoT libraries. Now, these libraries they're basically two. One is just a generic library, system device.gpio, that is mentioned on that slide. And that system device GPIO is mainly a way to interact with the pins on the board. So turning them on and off, handle power modulation, either software or hardware, if they support them. And it's not exclusive to the Raspberry Pi. That's also something important. All my demos today are going to be done with a Raspberry Pi, but it's not really something that you have to do in order to get to work with the .NET Core IoT libraries. Now, if you've never seen .NET running on a Pi, that I guess will be, it's not really a topic for this presentation, but it's something that I should showcase for you guys. Like on my machine, if I, and this is the Raspberry Pi itself. Let me exit here. So this is my Mac. I'm going to SSH into a Raspberry Pi that's actually on that picture back there. And all that I did to install the .NET tools on this Raspberry Pi was download from the Microsoft the .NET SDK for the ARM stack for this version. It was as simple as basically doing a curl command to download the tar file, extracting the contents of that tar file, and adding 2 lines of code to my local profile file to make sure that .NET was actually a tool that was available in my console time and time again as I logged in. So again, it's really simple. We could install either the SDK or the runtime. So yes, you can actually compile your binaries on a Raspberry Pi if you wanted to. There are reasons why not, though. It is a bit slower to compile on the Raspberry Pi because of the limitations of an SD card compared to an SSD disk that, for example, your big PC will have. But it's something to consider that you could actually do that. So if I check again, .NET version, the latest version 3.1.42 is installed. And if I check this SDKs, there's the 3.1.402. So I have both the runtime and the SDK on this machine. I'm not going to really use the SDK for the reasons I mentioned, but just so that you guys should be aware of that. So the other library, and mentioned in the slide, is the Iot Device Binding. And there's a lot of open source contributors that have actually made possible that library. If I go back to the website just to, again, showcase by teaching you where the resources are, if I click on this Iot Device Binding repository, took me to NuGet. Let me back that up. There's this huge list of supported device bindings that includes a ton of sensors and boards that are already out there so that we can actually use them. A couple that we're actually going to use today. So the demo that I'm going to build includes the use of a buzzer. So if on this device, this little round thing here on the top is a buzzer that's basically going to beep at some point when we do the demonstrations. We are also using, if we look through this list, a character LCD. So in this case, we're using LCD 1602, which is this device right here. And we're controlling this device, this LCD 1602, by using this Gpio Extender. This is a PFC 874X, and again, the simplest way to think about it, I mean, it's a microcontroller. It's basically sending signals out to GPIO chips that it has. Is that this is a GPIO extender? So basically, the communication that the number of pins that you had on the Raspberry Pi are not going to be affected when I basically work with this LCD screen. I2C communication is going to happen through this set of wires. There's only 2 wires that come into here that are sending signals. The other 2 are basically just the voltage and ground.
Roberto, there's a quick question I think is contextually important. How sensitive are the devices to static electricity? How should they be handled by hand? Christian asks.
Simplest answer I can give to that is I haven't burned one in 10 years. But yes, they are sensitive. I mean, most of the stuff that I work with are prototypes. If I was working with something that was, let's just say, a bit not disposable, let's put it that way, then definitely I'll be wearing a harness in my hand that would actually ground me so that I wouldn't be any problems. And I'll definitely be wearing shoes, which none of you needed to know that, but I'll probably be wearing shoes. So they're very robust, let's put it that way, but yes, they are sensitive.
And is that an anti-static mat that you have them on right now?
It is. It is. That is where I do most of my electronic work.
Okay, great. Thank you.
Yeah. All right. And again, most of the time on my presentations are usually dedicated to code. So let's jump right on it. We're actually going to go through this whole thing of we're going to write code to interact with an LED, going to write code to basically interact with a button and with a buzzer, etc. So I'll just go ahead and before I am told to do so, going to increase the font in Writer.
Yes, I could not unmute fast enough. Thank you.
Yes, yes. That's probably good. Okay, so let me open the other project, which is where, and all this information is going to be out in GitHub, but another project where I have some basic samples that I'm going to be running through. Now, the way I built this repository, if you guys wanted to do something with it later, is I actually put a tag on it with my starting point. So I'm just going to go ahead and just check out that tag. GitHub says I'm on a disconnected state, which, okay, that's fine. And let's start writing stuff. So there's this demo type enum. Again, I assume most of the people on the call are C# developers, so you're probably happy to see, hey, an enum, and we're going to be working with GPIO ports. So these are the demos that are going to be used. I'm going to follow actually most of the stuff that's actually here. And what they will allow me to showcase to you guys is, for example, how to work with a GPIO when using an LED and a button, and a buzzer, how to do power modulation, and an RGB LED, which has it already, which has power modulation, but we're going to be doing manually. So actually, this label is incorrect. This one's the one that actually already has the device binding in the library. The LCD, of course, it has a device binding, and we're going to be using I2C to interact with it. And we're not going to be able to use the temperature just because there's a bug in the library. I could have written a ton of code to do it, but ran out of time. But there's a bug in the library where the interacting with the DHT11 device binding doesn't work as expected. If you're curious to why, there's a one-wire protocol that is used to communicate with most temperature sensors, and that's what's currently broken in the IoT device bindings. Now, let's build the first one. There's a bit of code that I already wrote in order to not waste a lot of time while doing the demos themselves. So there's this wrapper, the static class program main, where I'm going to take in a parameter. The parameter is going to be one of the demo types, and that I'm going to execute within a task. And within that task, when a key is pressed, I'm actually going to go ahead and terminate the task. When working with hardware, you got to be very careful about how you handle multi-threaded code, in the sense that, remember, hardware is one and only. So when you're targeting it, you don't want to have two different parts of your code sending different commands to an LED bulb. You at least will get different results. Let's put it that way. Inconsistent. So let's go ahead and write that LED runner. So I'm going to create a method. I believe I could just write a simple run async. And I'm going to make sure to receive a cancellation token for it. Oops. Now, when this class is constructed, what I want to know is which pin my LED's on. So things that I will do here, I'm going to do a task.run. And within that task.run, I'm going to write the following code. I'm going to create an instance of a Gpio controller. Most of the demos are actually going to begin this way. I intentionally did not include the library, though. If we look at the website itself, going back to what we have here, the libraries themselves can be installed, if I go to the main README, by using the command line, so just doing the basic .NET add package. That's probably the fastest way to do it, but since I'm in an IDE writer in this point, I'm just going to go ahead and manage the NuGet packages. And I'm going to go ahead and do system device.gpio and just go ahead and install that on my console project. Now, it already identified that it existed, and I'm going to go ahead and say open pin, and I'm going to express my intention to interact with that pin. Now I'm going to go ahead and set that pin to low. Pin, to set that pin to be a output pin, because I'm going to be sending out electricity across that pin. I'm going to control the on and off. Now, at this point, I'm going to go ahead and just do an infinite loop, things that happen a lot in physical computing. And within the context of that loop, every time I go around, I'm going to check if the cancellation was requested. So in that scenario, I'm going to turn off that pin value low, and I'm going to break the execution, therefore completing this task. So what am I going to do within the loop, though, to showcase that this works? I'm going to go ahead and turn on the pin. Going to sleep for 250 milliseconds. And that should be good. So again, there's a lot of pipeline code just to make sure that the task is run properly and it can be canceled properly. But the nature of the beast is, in order to interact with the pin, you basically create a Gpio controller, set the pin mode, the pins are input or output. So currently we're doing output because we're going to basically be managing if it's on or off. When it's going to be the button example, which is the next one I'm going to do, we want it to be input, because we want to basically read from the port and determine if it's high or low in certain scenarios. So back to the program here, I'm going to implement that demo type. So that is case demo type LED. And let's do await new LED runner. And the pin. So so the easiest way to do this is a 3-bolt work that we're going to be doing, and I have, and it basically comes with every Raspberry Pi that you buy. The card that tells you where everything is. There are actually like things you can drop on it to give you better guidance of what is what. If you see my prototyping boards to this side, they already have like a breadboard. This is called an extender, which basically already labels all the pins for you. But in this case, we're going to do it a bit more raw. I'm going to take the board that we have right here, and I'm going to get 3 bolts, which if I follow the valuable card, it's on the first pin on the inside. So that is this one right here. There we have 3 bolts, and the ground is going to be 3 pins in. So 1, 2, 3 on the first slide. I know it's not too visual, but basically I didn't want to show you the fancy breadboards without showing you any of the manual work. And so we have ground and power there. I'm going to basically take the power, which right now is my black, and put it here. And I'm going to take my white wire, and right now I'm just using the Raspberry Pi as a power source. And as you can see, it turns on and off. Now, the difference from this to the demo is that I'm not going to be taking the power from this cable right here. I'm going to be moving this cable to a GPIO pin. And in this case, the GPIO pin that's easier for me to get is number 4. So if I follow the inside track, there's 2 5-bolts and the 4 pin. And I lost my ground there as I pulled, but here it goes. Let me choose another pin. 1 level down, that would be GPIO. Oh, my math was off. Okay, so there we are. So we have GPIO 4, 4th one down on this side, and we have the ground, which is the white wire. So now we're going to test out that code and see if the GPIO LED goes on and off. So,
Roberto, one piece of feedback: when you show the steps on the actual boards, can you make the video screen a little bit bigger? It's coming through clear. It's just a little bit small.
I know that the focus is not ideal. I also have a bit of a light here that might help a bit. Okay.
Great, thanks.
So the code for the sample, how do I get it into the Raspberry Pi? I'm going to use the SCP tool to get it up there. All that I need to do in that regard is I'm going to compile the project, and I'm currently on the root of the project here. I could program the UI to do this, the IDE that I'm using, Writer, but really this is a simple scenario. So let's go into the right folder, which I was not into. I'm in the source. I can basic samples there. So if I do .NET build, this should build a C# project. Now it's building it for the 64-bit stack that's installed on my machine, and I got a warning. Good to know. Missing the pin that I said I was going to put here, so 4, and then run a sync, and I'm going to pass in the cancellation token. And this is going to be the same for every single one of the demos that we add during the course of the presentation. So let's go ahead and try that compilation again. And I have a one-liner for this, but for the first demo, I figure I'd be a bit more verbose about it. So that compiles. Now I'm going to build a publish, content that I can push out to the Raspberry Pi. So basically what I'm saying there is .NET published this content and published it targeting that architecture, Linux ARM. And once I have that, and let's see it in Finder here, you'll see that on the AOT basic samples folder that I'm in, there is a bin debug folder that now has a Linux RM and a bunch of files, a great deal bunch of files that I will have to copy to my Raspberry Pi to get it to work. So I'm going to close this up and just going to go ahead and run the one-liner at this point. So basically I am publishing the app and also copying it to the Pi on the temp.0072 to the folder projects/basic. So my Raspberry Pi, I'm going to go to that folder. And I just see the content here as it arrives. And I'm just going to go ahead and press IoT basic samples LED. LED is the argument, again, just to figure out which one of the demos I was going to run. So yay, it works. So on the other demos, just to save some time, I'm going to be not detailing these steps as I did this time. So I'm not going to show you again, hey, this is the line that publishes the content. This is the line that copies it up to the server. So we're just going to focus on the code and how to interact with it. So the press any key to exit worked just fine. You guys saw my LED is actually out, which means, hey, the code that's managing the task actually worked. So let's go to the next one. And this is basically a button. I love to play with little electronic parts just to get an understanding about them. So the white cord at this point, or the black one, is actually my power, but it doesn't matter. Let me go ahead and put the ground over here and just go ahead and introduce a button to the project. Now, a button is basically a bridge where the bridge is either open or closed. Ooh, that's not good. Where the bridge is either open or closed at a certain point in time. So in this scenario, if I can get it in the breadboard, let's see, maybe it will work. So I'm going to do the same thing that I did before. I'm going to switch this to the 3-volt. I'm going to switch this to the ground. And as you can see, the button is basically, again, working in just being used as a, using the Raspberry Pi as a power source. So now all I'm going to do is, instead of going straight to power, I'm going to again go to that port 4.
Your command windows are blocking your...
And let's see. If you're OCD like me, well, I'm not too OCD, but probably it's driving you crazy that the black wire is passing in the BCC and the white is the ground at this point. But there it is. So we're not going to use the LED for this. I'm just going to move this to here. So what I'm going to do basically is check if the button is pressed. I'm just going to produce an output on the window. So back to code. And I'll just create a a button runner class. And a lot of it is going to be the same, so I'm just going to copy paste what's over here. Now this is the button runner. We are going to have a pin. We are going to be looping, but we're going to be looping for different reasons. This is going to be an input, and when we loop, we still want to have some sort of delay in there. 250 seems good, so that we only get the event fire 4 times per second. And all I'm going to do is check read the pin. If the pin value is high, do something. And all I'm going to do for this, I'm considering independent for what we did with the LED. Let's just go ahead and say button pressed. And as far as I can tell, that looks good. Go back here. Button runner. And this is still on pin 4 for just because that's the way it is on that board right now. So let's go ahead and compile this and send it over the wire to the Raspberry Pi. Like I said, I'm just going to use the one-liner. Amazing how computers work. This copy, without all the heavy of the network that constraint that the machine is at, so the whole Teams, used to take like 2 or 3 seconds, but it seems to be taking longer. So that's across the wire. And on the Raspberry Pi, this happens sometimes. Seems I got disconnected. Let's go ahead and SSH in there. Let's go to the folder, projects, basic. Let's run the basic sample, but now targeting the button. Ooh, seems I did it backwards. Seems like my button is already pressed. Let's see. I'm gonna move this over here. Or I broke the button. Go ahead and resend it. Okay, and let's try to get the action going. So I may have messed up the wiring here or there, but you get the gist. Basically, the reason why we were getting that information wrong at the first time is because what I'm passing into the button is the ground. So basically what I should be monitoring for is, am I getting low from the pin rather than anything else? So that's why it is working now and it wasn't working before. So, I don't know, that's great. Demo seem to be working. So next demo, and I'm going to bring in the big board at this point. Let's take this out. My Raspberry Pi likes to say goodbye when I do this to her, but let's see. I'm gonna go ahead and plug in the pins first here. A nice ribbon cable. There it is. I'm checking if I left any pins out on this side, any pins out on this side. Looks like it's good. Now I'm gonna take my ribbon and plug it into this board. So apparently I survived. If I can type here, all is well. So let me show you what this is. This is an RGB LED. Sorry, there it is. So this RGB LED basically has 4 legs on it. The 4 legs are, the big one is the common anode, so basically the ground in this scenario, and it has 3 different pins that control the RGB output. So is it red, is it green, is it blue? And that's how we're going to basically be doing power modulation. And I already have them set up in different places, but just to showcase that it's working, I'm going to unplug the R, which was on 18, and I'm going to plug it into the 3-volt directly. And that should, again, by just using power supply here, do the magic of bringing it online. So I'm going to put 18 back in, and 17 is blue, or green, sorry. And 17 went on. And 22. And 22 is blue. So everything is working. Now, the code for this one is going to be slightly more complex, but it's definitely worth seeing because this is basically what you're going to have to do as you're building custom hardware. So let's say, again, new class, RGB LED runner. And this RGB LED runner, there are a lot of things about it that I'm definitely going to need help from my snippets to get it working. But I can steal some of the infrastructure that we already have in place. So I'm going to go ahead and copy this part of this code right here. And I'm going to copy also how we end that code. But the in between, I'm not going to need here. So let's say goodbye to the controller, say goodbye to this, bring in the references. And like I said during the hardware showcase, there are 3 pins that are going to be of interest here. So there's going to be a red, there's going to be a green, and there's going to be a blue. Now let's get those 3 pins in here. And what I'm going to do is build, just because it's convenient for the demo purpose, an anonymous object called RGB. And I'm going to create within the context of that anonymous object what I'm going to need to interact with each one of those. So red is going to be software Now let's see if I get some help. Nope. Oh, I'm missing a library. Iot Device Bindings. Now here is where I'll find the software PWM channel. Thank you. Now that software PWM channel is going to take 2 variables in, I believe. Well, it takes more than that. We actually pass everything that we need on it. So let's say this one was red. This I read off the specs of the bulb. It works at a 2000 hertz frequency. And the duty cycle on it just means how that frequency is going to be handled. It's going to go from 0 to 1 in order to implement the color. So we're saying that by default, it's going to be off. Now, the other fellows here, red, green, and blue, modify the pins. Now, I'm going to start all those different software PWM channels. So blue, red, and green. And I'm going to basically bring in a method that's going to help me do some math. I don't want to be writing this while you guys are there, so I'm just going to go ahead. I do have this demo already up in GitHub, and I'm going to be handing this URL out for you guys. But there is this override.core, IoT.NET Core basic samples, and it's a simple math. It's not really something complicated. It's just not something I want to be typing. So Rgb LED runner, and here we go. Let's copy this little math right here. And as soon as you see it, you probably know what it is. I mean, it's an inline method here, but all that I'm doing is basically giving a number, which is going to be from 0 to 255. Those are the ranges I'm giving it in and max. Give me the equivalent of that number between 0 and 1. So it's basic math, and here's the formula. But I didn't want to type that out. Definitely, it'll definitely would have been stressful. So I'm going to also create another method, though, that takes in a color struct. There's not a lot of drawing support in .NET Core, but there is system.drawing.color basics. I'm going to be using that to say the following. RBG red dot duty cycle, it's going to be the following. Take the R of that color and, you know what, map it. So same thing for green and blue. Now, I guess you guys are already noticing the trend here. Like, what would I do in cleanup? Well, definitely I should send a color from Rgb where everything is 0, so everything is off. But what can I do to showcase it? I can probably just go ahead and do. Oh, and I need to, in cleanup also, stop them after I do the set color. So, oops. Not my best copy pasting effort. And for now, let's just say color the red and sleep for 250 nanoseconds. And green, blue, and yellow. Just to have one that's not part of the basics tag. And that looks good. Let's go to the program itself. And let's go ahead and add that RGB LED. Now pins. I think I read them off the board earlier for you guys. Like if you want to basically look at them again, I believe we have is 18, 17, and 22. So 18 is red here, and then green and blue are 17 and 22. So 18, 17, and 22. And there we go. So that should be good to go. Let's go ahead and copy that over. There'll probably be a bigger time copying the files across the network right now, just because I added a library. It's not a huge library, but it is a library, so there'll be a hit. Now, having the files there already, let's see what I got here. Do LED RGB. Now, double check I did that correctly. RGB LED. and let's run it. And there we have it. Merry Christmas in September. Now if I stop it, it should end and it should be up, so good. So I'm gonna skip doing the buzzer just because I don't think I would have time to showcase the last part of the demo if I do the buzzer. So I'll just skip that part and let me go ahead to my slides and the LCD too, but it's gonna be showcased in the last demo itself. So this is what I basically built for you guys. So I'm gonna put it back together.
Hey, Roberto, you have about 10 minutes.
All right. So I'm gonna put this back together real quick. Let me bring back that. Bring this back. I'm just gonna remove the ribbon on this side, which is usually safe. Throw this away, and have that component that's on that picture. Oh, my Raspberry Pi is not gonna like that. So here we have, and this is gonna be really hard to see the LCD, but here we have pieces of what I was demoing before. We have here an LED bulb. We have the button right here. We have the buzzer and the LCD display. All these parts are currently written using those techniques that I demonstrated. The only exception to that is probably the LCD. And I can show you guys really quick what it took to get that one working. If I go to my more robust solution that is trying to be more enterprise, and ironically, I'm in that same file. There's the LCD file. So in order to get the LCD working, as I mentioned before, and I'll use this one to show to go back to this side. So as I mentioned before, this LCD screen in the back has a PFC 874 chip and is connected via SPI back to the Raspberry Pi. So what that means in where I'm configuring it, what I'm specifying is in which bus the LCD screen is to connect over I2C. If I go to the Raspberry Pi and ask it to show me the devices that are connected to it in I2C, I see that there's a device connected on the 27 address. Now that's important when it comes to the configuration that I have here. Notice that I'm saying, hey, on the bus 1, there's only one. The device address is 0x27. And that is using, again, the chip that the controller that I said that I'm using, the PCF8574, which is, again, a Gpio Extender in this scenario. So now when I create my LCD screen, all the pins that I'm specifying here, 0, 2, 4, 5, 6, 7, 3, and 1, are not actually pins on the Raspberry Pi, are actually the pins, if we go back to the LCD, that are specified there. That line of pins that are here. This one doesn't have the numbers. That one on the bottom, I believe, does. It does have the numbers. Now, having done that there, I'm saying, hey, display the backlight and display the, and enable the display. And then through that LCD 1602 driver, device binding, I'm actually just saying, hey, on the position 01, write this message. So depending on the user. Now, how am I using all this hardware? Go to this slide right here. And the way it works is basically GitHub has webhook technology. So GitHub is actually posting a request to the RESTful API in my Raspberry Pi. And with that, I'm actually controlling the LCD display, the LED bulb, and the sound that is on it. So I'm just going to go ahead and for purposes of the demo, just go down one and go into the runner. The code is already here, so I'm just going to go ahead and run it. IoT.NET Core hardware run. So some configuration happened for that. I can show you. I'm going to disable that token later, but as you can see, I'm saving information here that says, hey, monitor this repository. Hey, this is the owner of the repository, and this is a token that you guys will forget you ever saw. Doesn't matter, I'll delete it. But now that I have that information on my environment variables, I can actually run this application. Run folder. There we go. And now this is running on my computer localhost folder. I'm gonna, just because I'm gonna interact with it with Postman, I'm gonna do ngrok and oops, wrong computer. Probably easier if I type it. So ngrok an HTTP for the localhost 5000. And there we are. So I'm going to take this address and using Postman, I'm going to post some information for it because I don't want us to be waiting for GitHub to actually provide us that. So I have the post endpoint that's exposed there. In fact, let me edit this so that it's pointing to the right one. There we go. And just to show you that I can reach that, the browser, I actually put Swagger in there so I can /Swagger and see the endpoints that are actually in there. So IoT.NET Core Build Monitor API, we have hooks and we have the status. And I'm gonna post a hook down to that API and I'm gonna tell it that the status is queued. So before I do that though, let's look at what's happening here. Now I programmed the LED. Let's see. Good. Let's go ahead and set that status to queued. And if you notice here, we have the light going on and off. And hard to tell, but again, it says queued and it gives me the time of day. The buzzer should be ringing. At this point, I think that's a bug in my wiring right now. But as you can see, it is working. And if I post, let's just say a failure, red light stayed on, panel says failed. And if I post a complete, let's say something happened that was good, you just see the light go off and the panel, apparently that's where the bug is at. Completed is actually, oh, because it's status completed. Let's try again. There we go. I was missing a D there, but completed and the date and time. So the goal of that example, I mean, that I've just showed you, and again, the code is all out there. I wish I had a bit more time to showcase to you guys, is basically to say that even with the simplest of parts, because this is basically components that come in any Raspberry Pi electronic kit that's out in Amazon for pennies on the dollar, it is really easy to get started up and running with the physical .NET computing and basically build something that is worth it. Maybe my goal eventually was actually to do this all in a prototyping board with soldering and maybe wrap it in a nice 3D printed case so that it became a bit more useful at my desk. So having said all that, let me see. Yeah, I believe that is it. So I'm definitely going to stick around. I don't know if we have a little time for questions, Scott.
We have a couple minutes. If you have any questions, please post them in the live event Q&A so they get captured. We know there's a slight delay, so we'll we'll wait a few minutes for that to catch up. But in the meantime, thank you, Roberto, for a great presentation. And if you have time, I know we're at the lunch session and it's lunchtime, but if you want to continue the discussion in the etc. track in Discord, that would be fantastic. We'll be in and out of that track all day in Discord, so that's a great place to go. Any questions? I don't see any new questions coming through right this second. We'll give it a couple more seconds, and then we will move on. Okay. Do you want to pitch that last slide there, Roberto?
Yeah, I mean, if you guys want to take a screenshot of a slide, this is the one that I would recommend you guys take a picture of. It has all the resources that I think we have mentioned through the presentation. So my blog, Infernal Red's blog, where a lot of this content is going to end up probably within the couple of next week. And it also has a link to the repositories, which I showcased to you guys that have all the code that is actually there. And if you have a Raspberry Pi at home and haven't found a use for it, this is definitely the time to get involved with it with very little friction.
Okay, Roberto, can you also, we'll post these links into the Discord channel, and also in the Q&A, we can make an announcement with those links. So thank you very much, Roberto. Appreciate it.